Okay, hello everyone. Today we are going to continue this one-stage match-step methods um, that we introduced last time, and in particular, I am going to introduce Adams-Bashforth method. Two Adams method as two examples of these one-stage match-step methods. Okay. So, and in order to do so, we will do two type of those Adams formula. One open Adams open formula, which is an explicit method for this. And then the second, we are gonna talk about Adams closed formula, which is the implicit form of these type of methods. Okay, so let's get started. Adams methods. So first, Adams open formula, which is explicit form of this one stage match step methods. Okay, so I just want to note something here as I'm going to show du over dt. This is the equation I have as f, u, and t. Okay, so this is the equation I have. Just a reminder that how I am gonna approximate it. Okay, so du in time. So du over dt, how we are gonna evolve it in time, we are gonna say at time n, I'm going to use time n for this, can be approximated as un plus 1 minus u at n over delta t, simple forward Euler method. And for f, what I'm going to do, I'm going to use the old values, right, of that. So here we are. I can use tn minus 1, tn minus until tn minus p, right? So those are all known in this explicit method. So for f at tn, what I'm going to do, I'm going to say it can be approximated as a coefficient alpha 0 times f at n plus a coefficient at alpha minus 1 at f n minus 1 plus all these terms until alpha minus p, the coefficient alpha minus p for function f evaluated at the step n minus p, right? So these are the old values of f at previous steps. I know all of them. I know fn, because I'm calculating un plus 1, right? So I know fn. I know fn minus 1. F is a function of u and t, right? So fn is going to be the value of f at u n and tn, right? So I know un, right? So I know un, it is from previous step. Tn is clear, so I will know fn similarly. So the same thing for fn minus 1, fn minus p. I know all these functions, all the values of this function. These are just the previous steps, right? So this is explicit form. I know ftn, I can just represent it as this function. This is a general way of showing that. And we can choose these coefficients alpha I to give us an order delta t to power p plus 1 approximation. This is what we had let me yeah, we can choose actually for that to give us 2p based on this, right? Based on this, we can choose that to give us that. So I'm going to write it down here. So we can choose it somehow to give us that, that approximation. For example, a third order approximation which is gonna be order delta t to delta t cube I think I made something wrong here. It's gonna be delta t p plus 1. For example, this one, for this example, I wanna say find a third order approximation, which is order delta t with p equals 2. So I go 2 in the back. So what I'm gonna go 2 steps in the back is un plus 1 equals 2. So I'm gonna put this here. I'm just gonna write these two. So I mean the original equation was un plus 1 minus un or delta t equals to f tn, right? So I'm gonna just take everything on the right hand side for un plus 1. It's gonna be un plus delta t, and for alphas I'm gonna choose these values, 23 over 12 f evaluated at n minus 16 over 12 f n minus 1 plus 5 over 12 f n minus 2. Okay, and you can double check this, but this is the form of third order approximation with p equals to 2. This is an Adams open formula, which is Adams explicit formula. So you know fn minus 1, you know fn, you know fn minus 2, and you can easily calculate, and you know un from the previous step, and so you can easily calculate un plus 1, which is the new u, the u at the new step. Okay, so this is how we can evolve in time for this approximation. This is a third order actually approximation, which is a pretty good high approximation, right? So you have multiple you have multiple steps here, unlike the previous one, which we are only going one step. You are going from n to n plus 1, for example here, as you see in the Rangakuta method. But here you have multi steps. You have fn minus 2 one step, fn minus 1, and then fn steps. So you have 3 steps with p equals to 2, and but only one stage, right? You don't have any intermediate stage between these two. You just calculate it at n minus 2, n minus 1, and n. Okay, so this is Adams open formula. We also call it Adams-Bashforth method or Adams open formula, which is an explicit form of that. So Next, I want to talk and show Adams' close formula, or the implicit formula for that. So you can see how it looks like. So let me get started here. Adams' closed formula, which is implicit. Okay. So again, I'm going to represent du over dt at Tn as un plus 1 minus un over delta t. But for f, what I'm going to do, because this is an implicit formula, I can use the value of f at the current step, at the newest step. So I'm going to use f alpha 1, fn plus 1, plus alpha 0, fn, plus alpha minus 1, fn minus 1, plus alpha minus p, fn minus p. Okay? So the difference is in this term, that I don't know this term, so that is why it is called implicit, because I don't know it. I have to use some algebra or other things, matrix algebra, to be, or iteration methods, to be able to find the value of fn depending of if it is nonlinear or a linear function. Okay. So we can choose alpha i's again to give us, to give an order delta t p plus 2 approximation. Okay. For example, a third order approximation with p equals to 1, meaning order delta t 1 plus 2, is shown here. un plus 1 equals to, again, I'm gonna bring this on the right hand side, rearrange the terms. I'm gonna get un plus delta t, and the coefficients I have are 5 over 12 fn plus 1 plus 8 over 12 fn minus 1 over 12 fn minus 1. Okay, so one thing I want to note is, as you see, both of these, let me see. The coefficients here are gonna sum to 1. 5 over 12, 8 over 12 is gonna be 5 plus 8, 13, minus 1 is gonna be 12, over 12 is gonna be 1. The same thing for the other one. So that is one point. And the other point is, as you see, both of them are third order approximations, okay? And one is explicit and one is implicit. And so this one is explicit, meaning I don't know the value of fn plus 1, because fn plus 1 is what? If f evaluated with un plus 1 and tn plus 1, right? And un plus 1 is something I want to find. I don't know what it is. I know un, but I don't know un plus 1. So I don't know fn plus 1. And so in order to solve it, we have to do some matrix algebra or do some iteration method, right? For example, for iteration, if you're familiar with these iteration methods, one simple thing is just a try and error. Okay, very simple engineering thing. But there are also some optimization methods. For example, Newton or other things, other methods that we don't have time to go through them. But through those optimization methods, if you have a nonlinear nonlinear equation, you can just guess something around like un. So you can just set un and then see, put it here, and then get a first approximation for un plus 1, and then put un plus 1 here, and then get another approximation here. And so you just continue this loop on and on until you converge to a kind of constant un plus 1. So your un plus 1 does not change in time, does not change anymore. So this is one simple way of solving this using iteration methods. Okay, but in general these are more complicated. Implicit methods, you need to, if you want to code these, you want to make a you want to write a programming code for this, for solving this, for example, in MATLAB or Python or other languages, this is going to be more challenging than explicit ones, because explicit ones are easy. You just know fn plus fn minus 1 and fn minus 2. Okay, so this was something I want to say. And the other note I have is we can use open and closed formulas as predictor correctors. Similar to other Euler, we can use them together. So one will be a predictor, like this one will be a predictor, un plus 1. I can just get un plus 1 here from the explicit formula, then put un plus 1 here, and then get another un plus 1. So it's going to be correction to that method. Okay, so this is an interesting way of combining these two methods together. And if you are interested into that, you can delve into that more yourself and look at the error, the discretization error, how to minimize that, how to improve your numerical scheme. Okay, so with this we have finished the time marching schemes that I wanted to cover in this course. We talked about one stage much step methods and one step much stage methods, right? The other way around. So we introduced the most commonly used methods in numerical literature, numerical approximation literature. And so now the last thing for this finite difference approximation that I want to do is to solve an example, a full example of full space-time discretization. Say you have a partial differential equation, and then you want to discretize it and solve it numerically. Okay, we have talked about spatial discretization, we have talked about temporal discretization, but how can we combine them together? So this is the main essence of this example that I'm going to solve this lecture, and probably it might take until the next lecture. And after that, we are going to go through the probably I will spend one or two lectures on finite volume method, and then we kind of talk about stability criteria of these numerical scheme methods that we briefly touched on, but a more formal way of doing that with von Neumann stability analysis, and that will wrap up the course. Okay. So let me start this example, final example of this part. Full space-time discretization. So I want to do this as an example. Approximate the following transport PDE, partial differential equation, partial differential equation using finite difference method. Okay. And the PDE that we have is a transport partial differential equation, transport equation, and that is partial U. I think I need a little bit of time for that. It is just a simple partial advection diffusion equation, advection diffusion transport equation. So it is partial U over partial T plus V partial U over partial X minus D partial square U over partial X square plus kappa U equals to F X T, where it is between X is between 0 and L and T is greater than 0, greater or equal to 0. The boundary conditions of this problem are U at 0 is a given number like U left, for example. And for the right boundary condition, I'm going to use partial U over partial X at L is 0. So these are boundary conditions. And U, X and 0, which is the initial condition, is given to be 0. Okay. So this is a problem I want to solve. Approximate the following transport partial equation using finite difference method. Okay. Say I give this equation to you and I ask you to solve it numerically by programming, by coding it to computer. Okay. So the first thing you need to do is to discretize it. You have to discretize it first in space and then in time, and then start coding it and solving.